Okay, for section 7.4, we're going to look at trigonometric functions of any angle. Up to this point, all of the angles we've looked at have happened to be acute angles, so less than 90 degrees. So for topic one, we're going to look at, sorry, there's a moth in here. We're going to look at finding the trigonometric functions when we're dealing with obtuse angles. Okay, so these would be angles greater than 90 degrees, or if we're going in the clockwise direction, less than 90 degrees. Okay, now we have this formal definition of what these trigonometric functions are going to look like when we let theta be just any angle, okay? So it says, let theta be any angle in standard position and let AB, so think of just like a coordinate point almost, let AB denote the coordinates of any point except the origin, okay, on the terminal side of theta. And then we're going to say if R equals the square root of a squared plus b squared, then we get the following image. Now, I do want to remind you, when you're dealing with an angle in standard position, you have to go back to 7.1. Remember, the origin is at or the vertex is at the origin. The initial side of the angle is on the positive x-axis, and then you sweep your angle open either in the counterclockwise or the clockwise direction. In the counterclockwise direction, you have a positive angle, we'll call it theta. So this angle that is drawn right here, this is in standard position, okay? So we have our initial side on the positive x-axis, we have our vertex, we have our terminal side, and we have denoted just an arbitrary point AB on the terminal side. And you can see how we swept open our angle, and you can see that we have this distance R. Now, just for funsies here, okay, let's pretend when you opened this angle, it created a circle. So like if you were to sort of follow this point, you keep sweeping this angle open, okay? If you were to keep sweeping this angle open, that point is leaving like the image of a circle. So if we were to keep sweeping this open, we would have a circle. So this point from the origin to this point AB, this distance from the origin to that point AB, assuming this is a perfectly drawn circle, which I'll tell you right now, it's fairly tragic. It's not perfectly drawn. Pretend it's perfectly drawn. But this length R from the origin to the point AB is technically the radius. So kind of keep that in mind. That's going to be really important soon, okay? So let's think about what this means, okay? Now, let me get rid of my circle. Just know that there is a secret imaginary circle, okay? Now, what happens is if you kind of drop down from this point AB to the x-axis, we create a right triangle, right? So you'd have a right angle right here. Well, this length from the origin to the side of the triangle that we've just created would be the length A. The distance from the x-axis up to that point on the terminal side would be B, okay? And it would be really easy to use this idea of a right triangle to figure out what R is, okay? So using the Pythagorean theorem, we know that R squared, which now kind of is acting as the hypotenuse, is equal to A squared plus B squared. Well, if I wanted to solve for R, I would take the square root of both sides, which would tell me R equals the square root of A squared plus B squared. So that's what's happening right here. Okay, they've really just used the Pythagorean theorem to come up with a value to create the length of R. Okay, so we have that. Now, what we're doing here may not totally make sense because there's something we're going to learn in a couple of videos. We're going to learn about things called reference angles. So when you have an obtuse angle like this, if you create an angle from your obtuse angle to the x-axis and call it something like alpha, you've created a situation where you have an acute angle. And later we're going to learn all about what reference angles are and how they work as far as the sine or the trigonometric functions. But for now, just know that what I'm showing you is legal. It may feel a little weird. We're going to prove it to ourselves in a few videos, okay? So with this idea of an obtuse angle that has an arbitrary point AB on the terminal side, we can say that the trig functions are as follows. Sine of theta is going to be the point B, so that kind of like that y coordinate, the B coordinate, divided by whatever R is. Cosine is going to be the point A divided by R. Tangent is going to be the point B or the coordinate B divided by the coordinate A. And then we already know cosecant, secant, and cotangent are reciprocals to the three main functions. So cosecant is the reciprocal of sine, which is going to make it R over B. Secant is going to be the reciprocal of cosine, which makes it r over a, and cotangent is the reciprocal of tangent, which is going to make it a over b. Now let's think about a couple more things. We were told flat out that AB is going to be some point on the terminal side of this angle except the origin, okay? So we can't be the origin, we have to be any other point. So that tells me that this distance from the origin to AB has to be something. It has to exist, so it's positive. So we know that R is always positive, okay? Now, as far as A and B go, we don't really know. These trig functions only work if the denominator is not zero. So you need to remember, recall, a trig function will not be defined if the denominator is zero. So we know R is not zero, and as long as A and B are not zero, all of these trig functions would be defined, okay? Now, one other thing that I have listed down here, so we've already talked about the denominators being zero. One other thing is, how would this all look if we called the point on the terminal side just xy instead of AB, okay? It's going to be important soon. We're going to start kind of thinking of it more as xy. We're going to build this thing called the unit circle, and knowing that that point on the terminal side of your angle is xy is going to be really helpful. So as you're thinking of AB, kind of in your mind say, okay, A is really the x coordinate and B is really the y coordinate. That is going to matter in maybe the next section, okay? So just don't kind of completely stray from the idea that this angle lives in the Cartesian plane. This point on the terminal side is really just an xy value, okay? Now let's draw or let's look at example one, which is going to force us to draw a picture. So it says, consider a positive angle theta that has a point 4, -3 on its terminal side. Okay? So we've got a Cartesian plane here. It says draw the angle theta. We know it's positive and we know a point on its terminal side. Okay? So the point on its terminal side is 4, -3. And remember, I just told you this is kind of like our point AB, but we're drawing it in the Cartesian plane. So know that the first coordinate is your x coordinate, the second coordinate is really your y coordinate. So to draw the point 4, -3, we would go from the origin to the right 4 and then down 3. So this point right here is the point 4, -3. Now we're really drawing a positive angle theta. And for an angle to be positive, remember you'd sweep open in the counterclockwise direction. So we're going to draw this in standard form. We have our vertex at the origin. We have our initial side on the positive x-axis, and then we're going to sweep open in the counterclockwise direction with our terminal side being right here. So this is theta, okay? Now we know from the definition that we just looked at that sine of theta is going to be b over r, and cosine of theta is going to be a over r. Well, given this point on the terminal side, we know what a and b are, but we don't know what we know what a and b are going to be, we should say. We know the values of a and b is better, but we don't know the value of r. And remember, the value of r is the distance from the origin to your ordered pair, okay? So we're looking for this distance right here. This is r. Now, we can find this just by remembering this definition. Hey, r is the square root of a squared plus b squared. That's fine. You can also just think of this as a right triangle, where this is 4, this is -3. So we can just use the Pythagorean theorem to find r, or you can use that definition. That's fine too. So we know that r squared equals a squared plus b squared. So r squared equals 4 squared plus -3 squared. Well, r squared is 16 and -3 squared is 9. So r squared is equal to, well, 16 plus 9 is 25. And if I take the square root of both sides, I get that r is equal to 5. So let me write that where it all fits. So r is equal to 5. So now looking at part B, it says, okay, find the exact value of sine and cosine. So if we want the exact value of sine, we already know from the definition above that sine is the ratio of b to r. So we know it's b over r. And from this ordered pair, we know that b is -3. And we just found that r is 5. So sine of theta is 3/5. Now, cosine of theta, we are told from that definition, is a over r. Well, we know from this ordered pair A is 4. We just found that R is 5. So cosine of theta would be 4/5. Okay? We're going to end up doing a lot of this where we kind of draw these angles, but we really just build a right triangle between the angle and the x-axis. Okay? Now, for example 2, let's consider the angle, that should say an angle. I have a typo. So let's consider an angle of theta equals pi over 2. Now, pi over 2 is radians, okay? Hopefully you remember that pi over 2 is actually one of your quadrant angles. If not, let's think about this, okay? So we know that if we have an angle that we never open up, so the terminal side is the initial side, that's just 0 degrees. Well, that's going to coincide with 0 radians, okay? Now, if we go all the way up to the positive y-axis, that's 90 degrees. The negative x-axis is 180 degrees. The negative y-axis is 90 more than that, so 270 degrees. And then if we go all the way back to the positive x-axis again, we get 360 degrees. And we already know that one full revolution in radians, you should remember this anyway, is equal to 2 pi. Okay, so let's figure out what the other quadrant angles are as far as radians are concerned. Now, hopefully, you remember from your work converting between degrees and radians that we did some work and we found that 180 degrees is equal to pi radians. Okay? Well, from 0 to pi radians is 180 degrees. Halfway from 0 to 180 degrees is 90 degrees. So halfway between 0 and pi would be pi over 2. Okay? So we have 0 pi basically, then we have pi over 2, then we have 2 pi over 2, which is really just pi, which then brings us to 3 pi over 2, which is 270 degrees. And then finally, if we get 4 pi over 2, that equals 2 pi. Okay, so knowing the quadrant angles as degrees is great, but you also need to know the quadrant angles as radians. Okay, now this one says consider an angle of theta equals pi over 2. So we don't have a point on the terminal side, we just know where the terminal side is going to live. So let's draw this angle. So we have the vertex at the origin, the initial side on the positive x-axis, and our terminal side, we know it's going to be pi over 2 is the size of this angle. So our terminal side is going to be the positive y-axis. Now, we need a point on the terminal side. And if you're not given a point on the terminal side, you can choose any point you want. But let's make it easy for ourselves. Let's choose 1 on this terminal side, okay? So if we were to choose, let's say this is where 1 is, okay? Then the x-coordinate, or A, is 0, and y, the y-coordinate, is 1, okay? We now have a point on our terminal side, okay? Now remember, we need to find R. We need to know what R is. We have our A and our B. This is A, this is B, but we need R, okay? And we were told at the beginning of this in the definition that R is the square root of A squared plus B squared, okay? So let's figure out what that is. Well, we know that A is 0, so we get 0 squared. We know that B is 1, so that's 1 squared. So R is equal to, well, 0 squared plus 1 squared is just 0 plus 1. So R is equal to the square root of 1, which tells me finally R is just 1. Okay, so we know that A is 0, B is 1, and R is also 1. Okay, now the directions here said find the exact value of all 6 trigonometric functions. Okay, so we have to kind of go back to that idea of this definition. So sine of theta, or well, let's not say theta. We know what theta is. It's pi over 2. So let's go ahead and let's go back to black ink. I don't know why I kept sticking with the blue. So we have sine of pi over 2. Well, pi over 2 is b over r, which is 1 over 1, or 1. Cosine of pi over 2 is a over r, which is 0 over 1, or 0. Okay. Tangent of pi over 2, we know is b over a. Well, b is 1, a is 0. We have a 0 in the denominator, so we would have to say that tangent of pi over 2 is not defined. Okay? Now, as far as cosecant, secant, and cotangent are concerned, they're reciprocals of the three main trig functions. So cosecant of theta is the same as 1 over sine, which is r over b, or 1 over 1, which is really just 1. Secant of theta is 1 over cosine, which is going to be r over a. Well, r is 1, but a is 0. So we know that, again, in this case, secant is not defined. Okay. And then finally, we want to look at cotangent of theta. Well, I just put thetas again. I meant pi over 2. Do you all ever scream at me while you're at home watching these videos? So pi over 2, pi over 2, and cotangent of pi over 2. Now, cotangent is the reciprocal of tangent. So that would be A over B, which is, let's see, A is 0, B is 1, so cotangent is 0. Okay? Be really careful with these quadrant angles. It's the quadrant angles where you're going to have situations that are not defined. Okay? Let's see, do I have another example here? I do. Okay, so what we want to do is we want to fill in the following chart with all of the quadrant angles. We already know what the quadrant angles are from radians to degrees. We already looked at that when we looked at example 2. So I know that 0 radians is 0 degrees. Pi over 2 radians is 90 degrees. Pi is 180 degrees. And 3 pi over 2 is 270 degrees. I also want to draw this, okay? So if we were going to be drawing angles, okay, remember 0 degrees would be over here, 90 degrees would be up here, 180 degrees would be here, and 270 degrees would be here. Let's pick arbitrary points that would land in each of these locations. So like we already know how pi over 2 is going to work. We just did the work for that. But let's say if we had 0 degrees, we chose the point 1, 0. We already know that we chose the point 0, 1 for 90. Let's say we chose the point -1, 0 for 180. And let's say we choose the point 0, -1 for 270. That'll help a lot as we do this table right here. We're going to fill in the value for the 6 trig functions for each of the quadrant angles. Okay? So let's get to it. Now, I'm going to go through this really, really quickly. So what I would say is at this point, pause the video, fill this table in, and then check back, let the video play to see how I do this. I'm going to go through it really, really fast though. Okay? So sine of 0 degrees. We're going to do sine of all of these, and we'll do cosine of all of them, and so forth. Okay? So sine of 0 degrees. We have the ordered pair 1, 0. Okay? Now, because of the way this is going to work, if we were to calculate r for all of these, it would be 1 for all of these, no matter what. Now, if you have any doubts about that, you can kind of go back up to this right here. Let's pretend we had a circle. What we're really looking at is r is the radius of this circle, and it's going to have a length of 1. It's kind of the same thing that's going to be happening down here, okay? If we were to create a circle out of this, we would know that r is equal to 1. Now, you can do r equals the square root of a squared plus b squared for each of these points if you want, but I promise you're going to get 1 every time, okay? So we know that sine of 0 degrees, we're right here, that is going to be b, which is 0, over r, which is 1, or 0. Pi over 2, 90 degrees, we're up here. We know that sine is b over r, which is going to be 1 over 1, which is 1. Now, if we're looking at pi, we get that b coordinate, which is 0, over r, which is 1, so 0. And then at 270 degrees, we get that the b coordinate is -1, r is 1, so we get that sine is -1, okay? Now, cosine is the x coordinate of these points, okay? So cosine of 0 degrees is 1 over r, which is 1. Cosine of pi over 2, we're up here. The x coordinate is 0, r is 1, so we get 0. At pi, we have that the x-coordinate is negative 1, and r is 1, so we get that cosine is negative 1, okay? At 3 pi over 2, or 270 degrees, we have that the x-coordinate is 0, 1 is r, so we get 0. Okay, so just remember sine is always the y coordinate of that point, cosine is always the x coordinate of that point, and then divide them by whatever r is. Okay, now tangent is always b over a, which is really y over x. So at 0 degrees, we get 0 over 1, or 0. At 90 degrees, we get 1 over 0, which is not defined. I'm just going to do nd. At pi, we get 0 over negative 1, which is 0. And then at 270 degrees, we get negative 1 over 0, which is not defined. We have that division by 0. Now, cosecant is always going to be the reciprocal of sine, okay? So if we're looking at sine here, we want 1 over 0. So cosecant of 0 degrees is not defined. If we look at 90 degrees, we have 1 over 1 for sine. So we'd have the same thing, the reciprocal of that still 1 over 1. So cosecant of 90 degrees is 1. Of 180 degrees, we have 0 over 1 for sine. The reciprocal of that is 1 over 0. So cosecant is not defined at 180 degrees. Okay. And then for 270 degrees, or 3 pi over 2 radians, sine is negative 1 over 1. That would make cosecant 1 over negative 1, or negative 1. Okay. Now secant we know is the reciprocal of cosine. Okay. So at 0 degrees, cosine is 1 over 1. The reciprocal of that's still 1 over 1. So secant is 1. At 90 degrees, cosine is 0 over 1. The reciprocal of that is 1 over 0. So secant is not defined at 90 degrees. Okay. Secant of 180 degrees, well, cosine is negative 1 over 1, which makes secant 1 over negative 1, or negative 1. And then secant of 270 degrees, let's see, cosine is 0 over 1. The reciprocal of that is 1 over 0. So secant is not defined at 270 degrees. And then finally, remember, cotangent is the reciprocal of tangent. And at 0 degrees, tangent is 0 over 1. So cotangent would be 1 over 0. So cotangent is not defined at 0 degrees. At 90 degrees, tangent is 1 over 0. The reciprocal of that is 0 over 1. So cotangent is 0 degrees, or is 0 at 90 degrees. Let's see, for 180 degrees, tangent is 0 over negative 1. The reciprocal of that is negative 1 over 0. So cotangent is not defined at 180 degrees. And then finally, if we're going to look at cotangent, we're going to look at cotangent of 270 degrees. Tangent of 270 degrees is negative 1 over 0. The reciprocal of that is 0 over negative 1. So cotangent is 0 at 270 degrees. So it's helpful. The more you can commit to memory, the better off you're going to be. We are going to be learning something called the unit circle in the next section, and it's going to give you a really nice tool to help you find these values. So if you can really get a good understanding of the unit circle, you don't have to put quite as much pressure on yourself for memorizing this, but the more you commit to memory, the better off you'll be, truthfully. Okay?